today's lesson is going to be lesson 4.1, and it's going to be Intro to Equilibria. By the way, I have very carefully chosen these two titles to introduce you to both the singular and the plural form of equilibrium. One equilibrium is an equilibrium. Several of them are equilibria. Very good. That's right. Very good. So, two reactions.
Are we writing this down yet?
Yeah.
Well, I thought he was introducing us, and then we were taking note.
So let's look at two reactions to consider. And the first we will consider is the combustion of hydrogen gas. And who could give me a description for, of hydrogen gas, correct.
We've never done that.
True, but I bet you can do it.
H2 plus H2O equals...
You're on the right track.
Well, H2 plus O2
Yeah, equals...
You got it, yep.
Sorry.
Very good, excellent. Very, very good.
Isn't that really just an addition?
It is, absolutely. Yep, so we have hydrogen gas plus oxygen gas, because it's a reaction with oxygen, and we classify that as combustion. And what would it yield? H2O. And, of course, how do we balance it?
You need two oxygens and they would... You need two hydrogen sets and it would produce two H2O sets.
Very good. And if you had preferred to put that as half an oxygen, that's acceptable. I like this better. Yeah. Yep. Yeah, I will grab a seat. Let's get this note down, then I will happily share it with you and happily discuss it with you. Not especially. I hope so. But we gotta stay focused if we're gonna. Probably not, actually, which is annoying. Okay, and then two, I want to look at the decomposition of gaseous water.
What does that sound? That white noise.
Oh, that's
My-
this thing. Every day.
Is it, or is it the fans on my computer,
No, it's that.
which are going crazy? Sorry about that.
No, it's this. Every time. I thought it was only me that.
That was louder than normal.
Well, my fan is also going quite nice. Sorry? Yeah, my fan is quite annoying today. But I've got my computer's doing a lot of stuff in the background. Anyway, decomposition of gaseous water, and what would that look like?
H2 plus O2, 2H2, 2H2O balance it.
Yeah, so two of these will yield two H2s and an oxygen gas. Yeah. Very good. Okay. Now for each of these, we could write a rate law.
Rate law sucks.
We can write rate laws for these reactions.
Why is the water gas?
Because when you burn hydrogen, typically you do that at high temperature, and so you get gaseous water. Though, if you did this with a condensing coil and you wanted to put that as liquid water, that's a fair reaction too. I've intentionally chosen gas here because I want these to match. Though you could do both. You could absolutely burn these, condense the water, and call the reaction producing liquid water. Or you could do it like we do here and keep it above 100 degrees Celsius, in which case it will stay a gas. Both are reactions that are possible. I've chosen this one. So, here we have two reactions, and we could define both of these as having a rate. Yes? Okay. What would the rate of the first reaction be? What would the rate of the first reaction be? Yeah. So one sec, guys. Can we? I don't know, but I just move it. I gotta get through this. Go.
Rate equals K times
And I'm going to call it K1 because we're going to end up with a couple Ks. So I'm going to say the first rate is equal to K1 times.
H2 in brackets,
Yeah,
and we don't know the order,
to some exponent. Good.
times O2 in brackets, some exponent.
Very good. And what would the rate of the second reaction be? It'd be K2. Again, I'm just picking, you could call it K whatever, but I'm choosing 1 and 2. And what would it be? Yeah. And obviously, speaking of this in terms of concentration's a little weird, but, well, we'll get into that. And I need another letter here, and I don't want to use O because O looks like a 0, so I'm going to say Q. Try and stop me. I could have used anything. Could have used L. I could have used Z.
Can you use P? Cool.
Sure. Yeah, you know it. There we go.
Are you my water boy today?
No, I am going to come watch, but I'm going to I'm going to drag a chair out there, and I'm going to sit on a chair. That's what I'm going to do.
I can just hand you my water bottle.
Yeah, no, absolutely. If I can just toss things back and forth, I will gladly be your water boy.
Can't use K.
Okay, now, by the way,
Actually, no, that'd be cool.
We've also been using those.
Yeah, I know.
But it's more.
here's the thing. Both of these reactions are real.
Since this is a competition, just for fast battles and buttons.
Both of these reactions are real reactions, and they can and do happen. So, that means that if you have a high temperature vessel, and you've got some hydrogen and oxygen there, it's going to combust, and it's going to form water. But some of that water will also want to decompose and turn back into these. Now, as it happens, which of these reactions do you think would happen faster?
Turn back
The
into
decomposition. The T2H2O.
Which one of these do you think is the reaction that happens faster, easier, more readily, that's
The
going to go more?
combustion.
Yeah, right? Think about burning hydrogen. Does it take a lot of energy to make that happen?
Oh no.
No, you put a little bit in there, boom, and it happens. Whereas, remember when we turned water into hydrogen and oxygen? We had to hook it up to electricity and let it run. That was a challenging process, right? Remember, did we do an electrolysis lab?
In like grade 9.
In grade 9?
I remember.
Yeah, but if you remember, it goes fairly slowly, right? It might take half an hour to get a little bit of hydrogen to appear. Whereas this one happens real fast, right? Does that make sense? So these reactions both happen, but they don't happen at equal rates. In fact, they happen at very, very, very different rates. Cool, let's talk about that. I wouldn't say there is a reason, no. Just happens. I would say as a rule, this reaction is very fast, and this reaction is quite slow. How would these equations indicate that? The fact that this is a fast reaction, how is that going to be reflected in this equation? Sure. Well, the rate equals a bunch of stuff. So how would this equation say, yeah, that's going to be a fast reaction? Because we said fast reaction. Yeah?
The constant would be higher.
Yeah, very good. Because it's a fast reaction, it'll have a high rate constant. that make sense? Now, does that mean that if the concentrations get low enough, that reaction couldn't eventually get slow? Eventually it'll get slow, but if you have a high rate constant, the reaction is going to start out being fast. Cool. We didn't really talk about this last unit, but does that make sense? You can learn about a reaction by looking at its rate constant. If it's a really big number, that reaction's going to be pretty fast. Whereas this one, since it's a slow reaction, we could predict that this rate constant will be, that's right, low. All the same, if you leave these reactions alone together, they're both going to be happening, right? But we would expect this one to go faster than this one, right? Yep.
Quite slow and
very, very, very fast. If it looks like a U to U, you could think ultra or uber or unfathomably, possibly unbelievably, unexpectedly.
why not just make your V like
Ultra.
ultra?
I'm going to keep thinking of U words. Undeniably. They're just all unwords, right? Which is, except for ultra, yeah. But I love a whole class of words which is like where we only use the modified version, but never the opposite. Like we talk about someone being ruthless, but we don't frequently talk about somebody being very ruthful or ruthy. We talk about somebody being like discombobulated, but rarely speak about the combobulated people amongst us. We talk about somebody being like there's just a lot of words like that where we use all these modified versions, but we never, you talk about somebody being unkempt, right? Messy, but you rarely say like, that's Orlando, that guy is kempt, right? It's just not a word we use. Anyway, I like those. I think slowly but surely as I age and become a person who walks around with a cane, I'm going to speak only in the opposites of common words.
What's your favorite word?
He's way
Oh, golly.
That's two words. Probably actually. Anyway, actually, technically. All right. So let's get to it. Okay.
So what's your favorite word?
I don't know. I want to simplify this. Let's go even simpler.
that might not be correct.
Let's imagine two reactions that oppose each other, and let's imagine them as nice, simple, first-order reactions. All right, can we do that? We're going to say that we have some reaction, A yields B, and we have its reverse. And what's the reverse of A yields B? B yields A. Very good. See, we're going to go nice and simple here. We're going to keep it easy. All right? And furthermore, I'm going to tell you their first order. By the way, tomorrow, we're going to learn about how you can actually learn about rate orders non-experimentally. The theoretical meaning of rate orders. Why are some first order? Why are some second? Why are some zero? We're going to talk about what that actually looks like at the atomic level. But today I'm just going to tell you these are both first order reactions. Okay? So these are both first order reactions, which means what will be the rate law here? Rate equals, whoa, go away, goodbye. Yep. And we're going to keep it first order, so we're just going to say no exponent. Does that make sense? And everything we're going to do right now would apply if it were second order, but we're just going to make it nice and easy. And then what will be the rate of this one? Very good. And we don't know anything about K. We don't know which of these is fast. We don't know which of these is slow. But here's the deal. Let's start with a maybe. This is like a subtle tribute but rejection of when I was in math in high school, it was very formal, and every problem you started, you had to say like, let X represent and say what it would represent.
Oh no.
Let Y you had to very formally lay these things out. And if you didn't, it was like they wouldn't even read your answer. So
Can I ask why is let's with an apostrophe when it's
let us. So it's a contraction of two words. Okay, let's start with a container full of only A. So if we start with a reaction container, a reaction vessel that only has A, this rate is as big as it can possibly be, right? K is constant, and let's say this container is very special, where it's going to keep the pressure constant, it's going to keep the temperature constant. We have this perfect ideal reaction vessel. It's going to keep everything constant. In that case, this reaction starts as fast as it possibly can go. Does that make sense? A is never going to be bigger than at the start here when we only have A. So we can say reaction 1 is going to be as fast as it can ever be. What is going to be true about reaction 2 right at the beginning?
It's gonna be slower.
In fact, how slow?
Very.
How very?
Almost not happening because there's not enough heat.
In fact, not only almost not happening, if we're considering right at the start, it is not happening. So reaction 2 is not happening. Right? Like at the beginning, only reaction 1 can be happening. What is going to happen as the reaction continues?
There we go.
That's for you, Chris.
I know. As soon as you put R.
As the reaction continues,
Oh my god, really?
No.
Use a different
Wow.
There's more. Okay, no.
Wow.
That's disgusting. That
That
is
is
gross.
horrible. Don't erase it. Don't erase it.
I can't look at it.
It's so bad.
That was for Chris's sake.
You know, like little R apostrophe C apostrophe N.
As the reaction continues, more A is used.
Mr. Orlando, is there a yellow spot on your projector screen? Like where your OBS studio is down at the bottom bar? Is that yellow?
No, that's actually on the screen. It is that the background is transparent, so you're seeing a bit of the background. Like that is what it looks like on the screen as well. It's because this taskbar is semi-transparent.
Okay, but is there looks like something dripping down the wall?
Oh, that. Yeah, that's coffee. Long story. I should probably clean it at some point, but it reminds me of a funny story, which I'm not going to tell right now, but I will tell later. So as the reaction continues, A is going to get used up, right? Because this reaction's happening real quick. So we're using up a lot of A and we're making B. So the concentration of A is dropping, but at the same time, more and more B is being made, right? What is going to happen then?
And more and B.
And do happen.
So as the reaction continues, more A is used up and more B is being made. What's going to happen to reaction 1? Eventually, well, maybe, but certainly what is it definitely going to do?
Slow down.
Yeah, reaction 1 is going to slow.
And that's when reaction 2 starts.
And reaction 2, as reaction 1 is slowing down, reaction 2 is going to speed up. But now keep in mind, if 2 gets faster than 1, more A will be made and more B will be used.
For someone with the ability to highlight words and move them to the side, you really seem to cram.
That's a fair point. I accept it. What I would say is if you, like me, have made your word more oddly small, you could just slide these aside.
Look at what you
And if you accidentally took not the 3-ish part of the B, you could take that with you and just do that. And then you could highlight your more and make it bigger.
With the really messy or next to a really neat.
There you go.
Who's so random? Now these are like all these colored pens.
You can't have enough colored pens. See? Yeah, there you go. All right, so look here. If eventually we get to the point where 2 speeds up so much that 2 is now faster than 1, well, if that's true, then A is actually going to be getting made faster than it's used, and B will be getting used faster than it's made. Which means then what's going to happen? Now, instead of 1 slowing down, 1 is going to and what will happen to 2? Slows down. And I hope I don't just have to write this over and over again, but exactly, these will just kind of flip-flop, won't they? Do you mean the on-screen keyboard? Yes. Yes, I can. Just throw it. Just huck it across the room.
Yeah.
No, I'm good.
Demonstrate your computer.
Ooh, well, may I say, a nicely used defenestrate. That was good. That was solid. To defenestrate is to throw something out a window. To auto-defenestrate is to throw oneself out a window.
There's words for these things.
Of
I
course.
enjoy how the English language has a word for throwing yourself out of a window, but it doesn't have a word for the day before yesterday.
That's a good point.
Is it really not?
2 days ago.
That's not a word, though. That's a phrase.
Oh, God. That's a word for second. A lot you say that before yesterday.
It's true. We have a word for second last, but not a word for 2 days ago.
What's second last?
Penultimate.
You've heard
I say this all the time. It's one of my favorite
trying
words.
to use it anytime.
Wait, do we crack the code?
Yeah, his favorite word's penultimate.
No, it's one of his favorites.
If you were to make a list of my favorite words, it might be the penultimate word on that list. If it were in descending order of appreciation for it.
Yeah, your favorite conjunction is nuts.
Okay, so that is true. Okay. Damn it. So let us now look at this graph and try to graph what we just described. At the beginning of the reaction, what was true about A, the concentration of A? It was as high as it's ever going to be. And we said eventually it lowers like this, right? And as that is happening, what is true about the concentration of B?
It'll start at nothing.
Yeah. But then we said at a certain point, maybe this point here, the concentrations are such that the reactions are actually going to start going in the... Can I what? No, not while I draw this, because I won't possibly be able to do it nicely, but once I'm done this. So look here, we said at some point, these reactions are actually going to reverse. But then, what will happen to them again? They will reverse again. And this can happen over and over and over again. But they will tend to get closer and closer to some steady state.
No, I see this.
Not yet.
Didn't those lines be intersecting?
Not necessarily. And I actually intentionally drew it like this because whenever you see it in a textbook, they always show them approaching equal, but there's nothing that says they need to be equal. What would be true about these equations if they met at the exact same spot?
Then they'd just be at the
These
exact
two
same
K
spot.
values would have to be
Same.
the same. But is there any guarantee that the forward K value is the same as the backwards K value? In fact, they're probably not. So where they end up is going to be a function of their K value. Does that make sense? The one with the bigger K value is going to end up on top, and the reaction with the slower K value is going to end up on the bottom. And we can even mention that, as we will do in a minute, but eventually By the way, have I shown you guys the newest thing the photocopier is doing? Which is just fascinating beyond all measure. Which is that every once in a while, when I print one of my anything from OneNote now, there'll just be random bits of it that don't print. So like look in that word, which is eventually, it has just printed some of the letters, but not others.
So being.
Yeah, just wherever, just and like no square, but that's all in the note. It just doesn't print.
Which photocopier was that?
Copier 2.
Of course.
Friggin' copier 2.
Arch nemesis too.
He is my arch
I like
nemesis.
how Copier 2 is slowly becoming our arch nemesis too. Like everyone.
Well, because it affects you, right? That's the thing is he hates me, but his hatred of me hurts you.
I heard rumors that he also hates Shelford. I don't know if Shelford makes sense.
When he said photocopiers, the war is the
Years.
Eventually,
Why don't we just get a new photocopier?
Yeah.
Which is my grade.
A will be made
I think that's like when I got
by reaction 2 at exactly the rate it is consumed by reaction 1. And when that happens, the reaction appears to be constant.
Wow. No. Thank you. Oh, take it back.
finally hurried up.
So at exactly this point, okay, sit down. Okay, so eventually, this will steady out. It will be perfect. By the way, if you felt so inclined, well, we'll get to that in a minute. What do we call this state? Well, it's obvious. It's in the title of the lesson. This state is called equilibrium.
The beginning of the
Singular, so brium. Equilibrium. There we go. So we say it's reached a state of equilibrium, which is plural. When you have more than one of them, this is my cat, these are my cats. This is my dog, these are my dogs. This is my equilibrium, these are my equilibria. I have named them all. Fluffy, also Fluffy. Fluffy 2, the sequel. Good namer of dags. Dogs. Why did that come out like I was from Buffalo? I'm good at naming dags. Got lots of dags. Okay.
Are we stopping here for today?
No. Good question. No. Oh, does it? Oh, no. So look here. So now, what's this mean? Well, you can tell me what this means, because at equilibrium, what will be true? First of all, the fact that the concentrations aren't changing at equilibrium, does that mean the reactions have stopped?
No.
No. What it means is that the one reaction, the forward reaction, where A makes B, is still happening, but at the exact same rate A is making B, B is making A, B is making A, making. B is making. It's that was really Russian. It's making. Da is making B. Anyway, I feel like that's a fraught impression to be doing right now, so we'll just move right on. If anyone has a small child in your life, you are familiar with equilibrium states, where you have reached the point where you are putting the left boot on at precisely the speed they are removing the left boot.
Yeah.
And it just switches.
You said the left.
You know what I mean. The point is that they are undoing what you're doing at a perfect rate of equilibrium, and you could just spend all day there if you felt so inclined, or you can just give up and let them go outside with no boots on. Or more likely, 1.
Or remove their arms so they can't take it off. Yeah, that works.
Parenting advice from Preston. We will keep it under advisement. Now look here. Look here.
So they don't need them.
Look here. At equilibrium, what's true? This reaction is happening at the same rate as that reaction, which means that this rate is equal to, and we all remember Euclid's first axiom.
Yes. I've never heard that in my entire life.
Euclid's first axiom, which states that two things that are equal to the same thing are equal to each other, which means that
You seem like
at
such a
equilibrium,
professional now.
this rate is equal to that rate, and if that rate is equal to that rate, then K1A must be equal to
K2B.
K2B. That's what happens at equilibrium. We find this state, and if we knew K, could we find the concentrations that satisfy that equation? Why, yes, I think we could. Does that make sense? It does. You're not wrong. That's fair. My Ks are not great. It's one of my many failings. So this is the big takeaway. This is where we're going to go. Whoa, 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 wow, it's getting heated over there at table 3. Do you know that in my head I've numbered the tables today?
What's table 1?
Oh, why did you not write it?
Why wouldn't we do 2?
4, 5, 6.
Where's the third table? What do you?
Why did you start writing it in the middle?
Because like this. Look.
Why are you writing in the middle of the page?
Because I'm going to put a box around it. Okay, at equilibrium. Don't judge me. There's a reason for things. You're table 3 because you're my third favorite. It's in the middle because I'm going to put a box around it. If you're wondering how I've numbered them, it's by how much I like the people sitting at them. I'll let you decide if it's an ascending order or descending. Either way, you're right in the middle. All right, so at equilibrium, we can say,
Well, you're my like you're just we're the best. Third best.
But you really like Tyler.
Ryan, you know, I always forget who was best until you mentioned it.
Sometimes I'd be like, why am I recording this? Yeah.
So wait, what's table 1? You still haven't answered that.
okay, Shh, we'll get the, okay, come here. Shh, look here. I would also like that. Okay,
Wrong with you?
which means, shh, look here.
That's not what I do.
Which means two things. One, it means that we could say this means that concentration of A and the concentration of B will be constant. But here's what it does not mean. It does not mean that those two concentrations will have to be equal. Because it's not A that equals B, it's K1A that equals K2B. They're both modified. They're modified by their rate constants. So don't make the mistake. The classic mistake, and the reason I intentionally draw this diagram with them not meeting in the middle, is because they don't have to be equal. They are equal to each other when multiplied by their rate constants, which is not the same thing. So, will be constant, but not necessarily equal. In fact, not even likely. Necessarily. There's no way that's spelt right. 2 S's?
Yes.
What? Why are you even AR there?
There's 2 C's.
And IL.
There's 2 C's, not 2 S's.
Oh, really?
Yes. It's CCA.
Yeah.
CC and
Oh boy, that looks wrong, but okay.
That's not airily. That's not airily.
Okay,
That's
repeat.
Aries.
Somebody look that up.
NECESSAR.
Oh, exactly how I had it! After I changed it the first time.
It's double C double S.
No, it's not.
Can you scroll up a little bit?
I choose to believe that I was right.
After I corrected you.
Tim, you just gotta take everything
That's
from-
true. I can't disagree with that.
You're just gonna take everything from him, though. Damn.
No,
How are
I'll
you
leave- I'll
not
leave it
first place
as-
on math?
Now, what you should logically be assuming here is you should be saying, Mr. Orlando, would it not be the case that I could then predict the concentrations at which equilibrium would be met if I knew the rate constants of these reactions? To which I would say, yes, Christopher, you could assume that. And then you might say, Mr. Orlando, would it be fair to say that tomorrow we will be learning how to do precisely that? And yeah, we will.
Unless
I won't be
Calvert
here.
takes another half period.
Yeah, well, I can't complain about that. I believe I took you out of data early yesterday.
Yes, you did.
By 30 minutes.
Did he give you a whole 30 minutes?
No, yours 20.
That was very generous of him. Wow. I just asked if he'd give me a couple minutes, but 30.
Yeah,
We
that's
left at
20.
12.
You know
I mean, maybe dude just didn't want to teach a whole period, which I get.
It was a short lesson, anyways.
Okay, so listen.
Just so you know, there's a monocle on the way.
Oh, God.
Is there really?
Yes, like a 1920s with a chain monocle. Someone else got a
He literally wore a jacket. At least he didn't have tweed elbows, because if he did, I would have cried.
Listen, if I had tweed elbows, you know I'd be wearing them every day. Okay, let's look. So, here's the key.
His
We're
shoes
going to
match
learn-
his cane.
We're going to learn that for any time you have a situation where there's a reaction and its opposite, both of which actually happen, then there's got to be a state at which they reach an equilibrium. A state where the reaction driving forward perfectly cancels out the reaction driving backwards. And when that happens, the concentration of A and the concentration of B will be steady. For something like exploding hydrogen, that is like 99% in one direction, because the one reaction is so much faster than the other. For all intents and purposes, all of that hydrogen is going to explode, and a very tiny fraction of it will be reconstituted as hydrogen. Like fractional, functionally zero. Does that make sense? But for other reactions, that equilibrium point might be right very much near the middle. If there's reactions that can undo each other, there will be some concentration of A and some concentration of B, and that's assuming there's only 2 species involved. If there's 7 species involved, it becomes a more complex equation. But that's what we're going to talk about tomorrow. And there will be some place where the concentration of each reactant times whatever it needs to be multiplied by will be equal to the other, and that will form an equation that you can solve. Now this is first order, which means it makes a very nice linear equation. And is solving a very nice linear equation easy?
Yeah.
Yeah, right? You could say, I'm going to pump in a concentration for A, we'll call that X, and then we'll say that this is
So
X
what if
minus
something's
like,
second order and
solve.
first order? Does that mean that one is now not like equal to the other, but it is like one is like one's like 3/4 of the way.
If one of them had been second order, then it would be K1A equals K2B squared, which is still an equation you can solve, but you're right, it will be a different shape. It won't be that perfect curve moving in, they'll be moving asymmetrically to one. But they will still reach a state of equilibrium. There's still a point at which they are equal. And like I said, tomorrow we're going to learn that when we said you have to derive whether something is first order, second order, third order experimentally, that's true, but it's true with a big asterisk on it. Which is to say, we're going to explain tomorrow why some reactions are first order, why some are second order, why even some are third order, though those are very rare, and how we can actually work with that without having to do any experimental work.
Did you knock your thing out of the hole? What would happen if you went to like go down? It would have
That's
just
a good
like,
question.
came
We'll
down.
find out. Oh, just came back. Okay. I feel safe.
Just puts it
Never
down.
feel
goes
safe.
down.
I'd like to stop talking about my cane. Anyway, so tomorrow we will deal with that. You should have gotten your test back. If you didn't, come grab it from me, and I will give it to you now.
I like how Preston pointed out that the cane matches your shoes.
I believe I was saying I wanted to move on from my cane.
Are you insecure about your name?
I'm not insecure.